Yes, hello friends. Welcome you all in this hands-on session, and this is hands-on session number 8 probably. And now we are going to write that the methodology sanction of your research article, and definitely that will be reproducible. And I believe that uh, now you are ready to write your article. You have uh, completed your calculations, computation part. You have data, and the data is converted in form of tables and in form of figures. Then you have the summary of your works, and you are now ready to write your research article step by step. So in lectures as well as some previous hands-on session, we tried to know uh, the basic components of laser and sorry, basic components of that literature, that research article, and how to write, and what we have to avoid or what we have to take care during this writing. So time to time we practice also, but practicing must be continuous, and then you will have one refined article. So some sort of things you will I will just give the overview what that actually this methodology section content contains, and how you have to write. So in my case, I am taking this an example of that lithium ion battery, and some related studies, but your case, your study uh, will be different from mine, and but this is the practice session. You have to start writing that methodology sanction which is reproducible, and which fulfills the criteria required by a referee. So in this hands-on session, we have what this focuses on what that reviewers expect then evaluating density function based computational methodology, and we will work with the system-based DFT calculation definitely, and produce paper ready methodology paragraph that meets publication standard. So this is the part of that is specific scientific writing of for computational material science research focused on DFT. I'm Dr. Mohan Verma, professor of physics, and the instructor of this course. So why reproducibility matters in computational science? So generally the critical review questions that the can I reproduce this work? So when your article is on the hand of any reviewer, then the first question it is so the first question asked by uh, the reviewer in his mind, that is, can I reproduce this work? So the single question determines whether your computational study will be accepted or rejected. Many otherwise excellent DFT papers fail peer review due to missing parameters, ambiguous workflow, and tool-specific omissions that prevent independent verification. Key message: so reproducibility, this equals scientific credibility, and without it even groundbreaking results remain unpublishable. So time to time I am giving emphasis on the reproducibility of a result, which is uh, actually by shown by your methodology section. So just again I am overviewing that the reproducibility in DFT calculation, and for that what you have to do, a truly reproducible DFT methodology allows many competent researcher to recreate your computational experiment and verify your findings. This require comprehensive documentation of every numerical choice and influence your result. So these are that basic components of any methodology section, and uh, which actually help the to reproduce your results by other readers or other author. So first, that is the code specification, and we know we have to use software name with version name. For example, this Sista 5.4.1 like this. So when you write your methodology section, take care of this, and write this person, even that the full form of SISTA, it must be mentioned in this methodology section. And then this numerical basis size set you have to mention, and the cutoff energy, for example, that that D8P and that cutoff energy in mass cutoff here we are using. So this mass cutoff is equivalent to 350 RY, like this in this SISTA, for SISTA, and for SISTA that WASP and other things might be little bit different. And this convergence criteria we have to mention, and then exchange correlation function, generally that ZZA or with this PBE with the reference number we mention, and the sampling parameter, that is the k point maze, for example in three-dimensional case that is 6 cross 6 cross 6. The planar structure we can take 6 cross 6 cross 1, and that vacuum along in a specific direction, that is this z direction, that is to 20 angstrom. So this and the convergence criteria we mentioned there. And for even for this k point meshing, it's different in different part, that is in optimization part, geometrical optimization we use this k point, and for electronic structure calculation, DAS, PDAS, and that band gap, we use that some denser k points like 12 12 12 or 18 18 18 24 24 25. Now the relaxation protocol, so optimization methods and tolerance, it must be mentioned in this methodology section. Now some acceptable methodology section, the autonomy of that. So generally reviewer expect methodology section to follow a logical standard structure. Deviation from the stabilized order creates confusion and raise concerns about methodological. So even the people just try to change that order of that methodology section, but a specific order should be followed during writing this one. So we start with that code and the theoretical formulas, so that specify that DFT implementation and specific software version, and also that the foundation theory, for example that case Consam case theorem, like this. And then second, that structural model definition. So you are starting with that semi-specific unit cell or primitive cell. So when we start with unit cell and move to that super cell, so one should use the super cell dimension, periodic boundaries, and the system geometry. This must be mentioned. Even that number of atoms in that super cell, it is mentioned in this structural model. Numerical parameters like basis sets, cutoff, k points, and functional choices, these are the numerical parameters, and this must be mentioned in the third step of this methodology section. And then the geometrically optimization, so the relaxation algorithm, force tolerance, and the convergence, this is mentioned thereafter. And then this property calculation, just for electronic calculation, optical or transport calculation, this is given in the fifth part of that in the sequence in the method section. And then this validation and verification for presence convergence test and literature comparison, it is mentioned in the concluding part of that methodology section. So dear participants, keep this structure visible throughout the session as your methodology template. So this is the template methodology. So when you start writing of your methodology of your paper, write that in this sequence and submit in the group. So this is just one formal assignment, and even during discussion we can discuss about this. So now let's start one by one. So that is step number one. Step number one is that code and theoretical framework. So that the opening sentence of your methodology must immediately stabilize the computational framework. Reviewers needs this foundation before evaluating any subsequent details. For example, DFT formulas state whether you are using CONSAM, DFT orbital, free DFT, CONSAM DFT, or orbital free DFT or other variant, you can mention as a DFT formulist. And even that in my case, that I read that DFT implemented in SISTA and other things. So consum, and then this software identifiers provide a complete code name. For example, SISTA not AB initio code or first principle based code. You have to use that SISTA WASP or other things, even that full form the things, and even the version specification. For example, SISTA 5.4.1, just previously mentioned that, and also that the pseudo potential type clearly norm conserving, ultra soft or projected augmented wave pseudo potential to be mentioned. Even in the previous lecture I also mentioned different names of the pseudo potential. And now start writing your opening statement, opening sentence in of that methodology part. So write your opening in 2 sentences beginning with this: all first principle calculation were performed using, and write that DFT formulation, software name, versions, and pseudo potential, and for your material, with your tool. Then step number 2, that is exchange correlation functional and basis sets. That is step number 2. So what we know, that the exchange correlation function, this is specify that exchange of a function like LDA, GGA, GGA with PB and GGA with PB sole, that hybrid functional like HAC06 or other, include justification for your choice based on the system type, metal, semiconductor, or molecules. So if you are using that GGA PB, then why you are using, you have to write there. And the basis set specification for LCAO method like SISTA, we state the basis type as single zeta, double zeta, double zeta polarized, single zeta polarized, triple zeta polarized, and this each choice affect accuracy and computational cost. So clearly, even you can get when you are running your program, so you need to use one input file that is in form of FDF file, and all these parameters you are using are listed there, and use those parameter what you have used during that optimization, as well as calculating different properties. So copy from that one. So you do not write randomly, mimic that point from input file to this method section. And then this mesh cutoff energy. So this real space mesh cutoff determines numerical precision. Typically values range from 200 to 500 RY depending on the element type and requires accuracy. Always justify your choice. Even in some hands-on session where I have explored that in my team, in my group, how I generally start writing that research article. So the 3 to 4 hands-on session I have devoted to that, and that is for my research group, and I am sharing to you in this particular course. So that is my practice. So why I am selecting that specific cutoff energy and other things, that is known as the convergent test. So here you can mention that one even in the form of that plot and other things. So for example, this is that SISTA example. So XA functional, GGA PB, basis at DZP, mass cutoff is 300 RY in my case. So in your case, what will be the parameters you have to mention? So fill in your specific parameter value following these structures. Now the structure model description is step number 3. So again, this is actually the quantitative specification which is required to complete that method section. So the WAG structure description are primary reason for manuscript rejection. So reviewers cannot reproduce calculation without precise geometrical information. So give that the precise geometric information. For example, provide exact multiple of primitive cell, that is 3 cross 3 cross 1 supercell, that is containing number of atoms 27. This was constructed rather than a supercell was used. This is not, this is just a vague statement. So you have to clearly mention the dimension 2 cross 2 cross 1, 3 cross 3 cross 1. Even in several papers I mentioned that the primitive cell is there in a figure, and then that it's a super cell that is 2 cross 2 cross 2 or 3 cross 3 cross 2. It is reported there. And also that the vacuum thickness, so in two-dimensional materials especially, that is like a slab, surface slab, you have to specify the vacuum separation. So that start with a 15 angstrom to 20 angstrom. So mention, and also the mention the reason why you are creating the supercell and why you are creating this vacuum, because you just want to prevent that interlayer interaction, so that this 20 angstrom or 15 angstrom vacuum thickness is there. And also that if you are creating, you are doping something or creating defects, then also you have to mention the concentration of defects, how many defects you have created, how many atoms you have substituted. So, and also that the concentration rate or the defects rate can be mentioned in percentage. So this substitutional doping at 5.56% concentration provide the supercell context that reviewer actually needs. Now, for red flag for the reviewer, that is this type of sentence: a supercell was constructed. Just you're writing the single line statement, then no, this is not a good writing style. So avoid this type of things. Acceptable alternative, you have to mention that 4 cross 4 cross 1 supercell with the total number of atoms 64, lattice parameters A, B, and also that C is equivalent to 20 angstrom, and out of this 15 angstrom is actually the vacuum that was created. Now the k-point sampling methodology, so that generally in SISTA we are using this Monk-Hurst pack grid, state the explicit mesh dimension, that is actually in the reciprocal lattice system. So that 6 cross 6 cross 1, it's that the k-points, and you're writing just a dense sampling, this is not enough. You have to clearly quantitatively give that the k-point mention. And also that zeta point justification, if you are using just a zeta point, means 1 cross 1 cross 1 k points. So uh, so you have to use the reason behind that. For example, for the molecular system, if you are using some glucose molecule or some benzene ring type things in chemistry, and you want to optimize that, then you are using that bigger simulation box there. So the larger supercell there, then you can calculate this for the zeta point, means 1 cross 1 cross 1 k points. And also that the convergent testing, so reference your convergence study or with that cited literature value. And also that direction specific choice for anisotropic system, just justify different sampling density along different exercise. For example, then in three-dimensional we take that 6 cross 6 cross 6, 7 cross 7 cross 7, and for two-dimensional we take that 6 cross 6 cross 1 in this case. And also if we have just a single tube, nanotube like carbon nanotube, then we take the periodicities along one axis. So we take that 6 cross 1 cross 1 like that. So critical principle, k point density determines electronic structure accuracy. Insufficient sampling leads to incorrect energies and properties. So for DOS band type electronic properties, we take dense k points. Now step number 5, geometry optimization protocol. So that optimization algorithm, so this generally in SISTA we use that conjugate gradient method with sufficient CG steps. So I generally CG steps use in my system. So insufficient numbers of CG steps are used to optimize the system. That is optimization algorithm. Quasi-Newtons, that is BFGS, or molecular dynamic based annealing, each has a different convergence characteristics and computational cost. So clearly you have to mention this optimization algorithm in your system. And that force convergence criteria, so state maximum force threshold, typically we take that is 0.01 to 0.05 electron volt per angstrom depending on the required accuracy. So I take 0.05 or 0.04 electron. And tighter criteria needed for phonon or transition state calculation. Remember this. So that just 0.001 like that. Stress tolerance. So for the variable cell relaxation, so generally in my cases, I rarely use this one, variable cell relaxation. Uh, in the variable cell relaxation, not only that structure is relaxed, but also that vector, lattice vector is also relaxed. So there that the convergence commonly given in terms of that the pressure, so 0.5 to 1 GPa. That's omitting this part, cell optimization in a major methodology. Cell relaxation constant, clarify whether atomic position only and cell parameters and both were relaxed. State any symmetry constant and fixed atomic layer explicitly. So sometimes we have one bigger supercell, and out of that we fix that the bottom layer of this is the fixed. Then we should mention that the bottom layer is fixed and other atoms are free to move. So that is that relaxation criteria. So one example from SISTA. So structure were relaxed using the conjugate gradient method until all atomic forces were below 0.01 electron volt per angstrom and the residual stress components were less than 0.5 GP. So here that variable cell relaxation is used. That's why that GPa is given. Now step 6, so electronic self-consistence field convergence. So that SCF convergence parameters determine the accuracy of your electronic structure solution. Insufficient convergence leads to unreliable energies, forces, and electronic properties. So we have to mention all these in our methodology section. So SCF tolerance, density matrix tolerance is 10 to the power minus 6 to 10 to the power 4 to 10 to the minus 6. So this tolerance I generally use 10 to the minus 4, 10 to the minus 6, and that mixing, that is a mixing scheme. So specify this that the polybromine from 0.05 to 0.2 and some this actually control that SCF convergence stability, and all these the terms that is based on that mathematics behind that DFT theory. So that what is that polybromine and other things, SCF convergence, and also that the iterations, maximum iterations. So that is SCF cycles limit 500 to 50 to 200. I generally take this as 300 and for non-convergence calculation, and generally I use this 300, but we can save computational time by taking that in this range 50 to 200. So this is that example, sister keyword example. Tolerance is this, mixing weight is 0.1, 5 pulley, and that maximum iteration is 100. And then add all these specific values to your methodology drop, adjusting based on your system complexity. If you're writing two different papers and with a different parameter, then write it all these parameters suitable for that those system. Now the property specific calculation setting. So this all these are that is for the optimization, and after optimization we move for the property calculation. And for property calculation we have to clearly mention the things according to the property under interest. So they were expect clear distinction between structural relaxation parameter and subsequent property calculation. Different computational tasks require different numerical setting. One essential rule, so dedicate one paragraph to each property type to avoid methodological ambiguity. So even that in all these that 6 steps, you can use one paragraph or two paragraph, and that the 7th paragraph steps you have to use in a separate paragraph. So DOS and battery structure. So here that high symmetry K path for the band calculation, and for density of state that denser K point is used, and also that energy broadening scheme is used, and that for energy elastic band NEB, the report number of images, spring constant, force converging criteria, or climbing image implementation for transistor state. If you are using that AB initio molecular dynamic simulation, then that time step size, thermostat or barostat type, equilibrium time, production run duration, and trajectory, sampling frequency. All these parameters one have to use. For optical properties, so we have to use that polarization direction, scissor corrections if any, and the frequency range and the post-processing process, even some mathematical formulation uh, which actually helps to calculate optical properties is can be mentioned in this optical properties, how that the mathematical fundamental controls these optical properties, and how other optical parameters can be calculated by using that this dielectric function. And this validation and reliability verification, so demonstrating that your numerical choice produces reliable results in non-negotiable. Reviewers needs evidence that your parameters are converged and appropriate. So that the convergence, generally in my case, I use the convergent test for that energy curve cutoff, that is mesh cutoff, then k point, and also that that lattice variation, then final variation. So that energy cutoff convergence. So here even we can demonstrate this in form of a different graph. So the key computational parameters were systematically tested by convergence. The chosen 300 RY mesh cutoff produces total energy within 2 mega electron volt per atom of 400 RY calculation, whilst the 6 cross 6 cross 1 K points mesh converge formation energies to 5 milli electron volt. Calculated lattice parameter age equivalent to 3.18 agrees within 1% of the experimental value. So all these three parameters, in my case also, I use this convergence test, and I can write like this. Even that this converged lattice parameter, we verified, validate this result with some curve fitting like Kernaghan curve fit and other things. So all these I have discussed in how I prepare my research article. There in detail I have given in that hands-on session. So go through that and even try for your own manuscript. Remember this. Generally, some common reverse complaint. What triggers rejection? First, that missive missing information, sister calculations without version number. Reviewer cannot verify without availability or reproduce setting. So generally, even that people avoid these things, but one should write the version of that system. And also that force tolerance reported impossible to access with the restructured properly optimized dense key point mesh without numbers. Reviewers cannot evaluate electronic structure and unjustified u values. So if you are using u parameter, then how you select this u parameter? So the details of that convergent test of this u parameter based on that band, the tuning of band gave for that magnetic moment, etc. Inconsistent parameters, so missing results from different basis sets are functional without proper justification. And the critical principle for participants, remember this: if it is not written, it didn't happen. So reviewer evaluate only what appears on your manuscript. Computational details that seems obvious to you are invisible to reviewers without explicit documentation. So please, I request all participants during writing of this methodology section, you have to take care of each and every required points which is required to reproduce your result. One example, one polished methodology paragraph I am reading between the lines. So the all calculations were performed using density functional theory as implemented in SISTA code. Version is given 4.1. The exchange correlation iteration were treated within the generalized gradient approximation, that is GJ, using the Purdue-Burke Ernst-Hoff, that is PBE, GJ PBE functional. We implied Trulier-Martin norms, that is TM norms, conserving pseudo potential, and this is double zeta plus polarization basis set. A real space mesh cutoff of 300 RY and a 6 cross 6 cross 1 Monkhorst pack K-points grid were used for billion joule sampling, reciprocal lattice. And structure model consisting of 4 cross 4 cross 1 supercell containing 64 atoms with 15 angstrom vacuum separated when fully relaxed using the conjugate gradient method until residual force were below 0.01 electron volt per angstrom and stress components were less than 0.5 GPa if you are using that variables. Electronic self-consistence was achieved within that DM tolerance density matrix tolerance of 10 to minus 5 implied fully mixing with weight of 0.1 and convergence of total energies within respect with respect to K points density and mass cutoff are verified within 2 milli electron volt per atom. So this paragraph actually addresses all essential reproducibility requirement, software version, theoretical framework, all numerical parameters and value, and also that optimization protocols with tolerance and validation statement. So write your methodology section, frame this type of sentence and submit in the group, or during discussion session we can ask to share your screen and we can check how you are able to write this or not. So checklist before submitting your methodology to me. First, if any item below is missing, major revisions or rejection is required. So you can reject yourself uh, before submitting to me. So first, a code and a theoretical framework. So code name clearly stated, code version, exchange correlation functional and pseudo potential type, non-conserving alters whatever. Second, that numerical parameter, basis set types, SZ, DZ, DZP, real space, mass cutoff, K points, sampling, zeta points if with justification if a big supercell are used. Structure method, supercell dimension, vacuum thickness, doping or defect concentration, atomic position concept clearly stated. D. Geometry optimization algorithm, conjugate gradient or molecular dynamic simulation type thing. Force convergence, stress tolerance, cell relaxation. SCF convergence like SCF tolerance value specified, density matrix is scheme, maximum SCF penetration and spin treatment for polarized and polarized for spin orbit coupling or magnetic properties analysis, if any. And some advanced reviewers check frequently overlooked details. Uh, that F, that property specific reproducibility, DAS bands. So K path using high symmetry band for NAB calculation, number of images for MIAD, AB initial molecular dynamics, time mistake, thermostat types and simulation duration, optical calculation, that polarization direction or post processing method described some math, and validation of reliability evidence, K-point convergence, energy cutoff convergence, Humbert U value and the calibration of that U value, structure parameters compared with experimental one, that the latest constant and other things. And for data transformation workflow logic, initially structure source clearly experimental optimized or from the literature, and also final relaxation structure available for our failure described. Computational workflow presented in some logical order. Even you can give one proper flow chart how you started and how you get, and parameters remain consistent across related calculation. No mixing of result from incompatible computational set. So if out of this checklist 90% more than 90% boxes are ticked, then it can be accepted or minor revision. If 70 to 90% boxes are ticked, then these major revisions are required. Significance methodological gap exists. And if 70%, less than 70% boxes are ticked, then this the reject methodology, that is unclear, too many critical details missing, work cannot be reproduced or properly. So judge yourself, review yourself. So write one methodology part of your own material research and validate or review or that methodology section by this checklist, and submit the result to the group, whether you are accepting your methodology or you need minor revisions, or that your methodology section is required major revisions or rejected. You can judge yourself. So reverse perspectives as sovereign truth, a beautiful result with irreproducible matters scientifically meaningless. So this statement captures the fundamental principle underlying computational peer review. Reviewers encounter groundbreaking discoveries regularly, but without reproducible methodology, these results cannot be validated, built upon, or trusted by the scientific community. Your computational finding, regardless of their novelty or importance, will be rejected if reviewers cannot independently verify your methods. So the methodology section is not a mere formality, it is the foundation of scientific credibility. So becoming the reviewer, mm, you can become the reviewer of your own paper by following this hands-on session. And first, you can exchange your job to your partner with a small group, and apply the checklist. You can apply the checklist for others papers, and also other can apply for your paper. Identify the gap and some missing parameters, what are the missing parameters, and rewrite that critically, and then submit finally to the group or for ready for the discussion. So final message is self-assessment before submission. So if I cannot tick every item in the reproducibility checklist for my own manuscript, reviewers will notice it immediately. Remember this. So presentation over correction. Before submitting your computational work, perform the self-assessment rigorously. So writing complete methodology initially, it fare easier than reconstructing missing details during revision. Build the habit. So maintain detailed computational logs as your work. Documentation before effortless when integrated into the workflow. And respect your results. So uh, your computational discoveries deserve methodologies that allow them to the. So this session is complete. If you now possess the framework to write methodology section that meets the highest standard of computational material science publishing. So if you're getting more than 90% marks in your evaluation, then that is all the best and congratulations. So practice yourself. Thank you all, and I believe after this hands-on session, uh, this is not just the lecture. I tried to mention each and every minute contents of your methodology section, and I believe that you will get more than 95% in writing your methodology. So maintain that methodology writing workflow. Thank you all. Practice well, learn well, and happy learning.